To make a diffusion model accept new inputs, like a depth map or text prompt, you typically must build that capability from the ground up. Fine-tuning networks from scratch for specialized text-to-image models requires massive datasets and immense compute. It places a severe financial and engineering burden on anyone trying to adapt them. The traditional alternative to full retraining is classifier guidance. Instead of baking instructions directly into the generator, you pair a generic diffusion model with an external classifier that scores and nudges the generation process. But standard vision networks train on clean images, while diffusion models sample pure noise. To bridge this, the classifier is retrained from scratch on heavy static. Once trained, its categories are locked in. You cannot change targets without restarting. Currently, the standard workflow forces a strict binary choice. Accept the rigid limitations of a pre-trained model, or invest immense capital to build a specialized one from scratch. In 2023, researchers from the University of Maryland published a paper titled Universal Guidance for Diffusion Models. They proved an unconditional diffusion model can obey constraints from any arbitrary frozen vision network. Here, an off-the-shelf MobileNet model acts as the guide, forcing the diffusion model to turn an abstract purple silhouette into photorealistic dogs standing in snow. It maintains strict structural compliance across environments, generating those exact same dogs submerged underwater. It remains equally effective outside photographic realism, rendering the output perfectly as an oil painting. Not a single weight in the diffusion generator or the MobileNet guidance network was updated to achieve these outputs. Both networks remained entirely frozen. Using these off-the-shelf networks requires a method for bridging the data disconnect between the noise of the diffusion process and the clean inputs expected by the guidance networks. The primary bottleneck preventing zero-shot guidance is the domain gap. A standard facial recognition or object detection network explicitly rejects static filled arrays. We have to look at the baseline unconditional sampling step. A diffusion model acts as a learned denoiser, predicting the exact value of the noise, represented as epsilon theta, added to the data point at a specific time step. Because the model isolates that noise component, we can mathematically subtract it from the noisy state. This gives us an approximation of the fully denoised clean image at every single step of the process. This estimate is called z-hat-0. Extracting z-hat-0 acts as a universal bridge. Instead of feeding static to our frozen network, we pass it this clean estimation. The network can now analyze the image perfectly. The frozen network evaluates how closely the image matches the target prompt, calculates the loss, and generates a gradient vector. We take that gradient and inject it directly into the original noise prediction. This physically nudges the generation trajectory toward the user's prompt. The authors term this forward guidance. It hacks the model's internal noise prediction to align with external rules without leaving the natural data manifold. Forward guidance works well, but it has a specific failure mode. It frequently over-prioritizes the realness of the image and ignores the user's prompt. A practitioner cannot simply increase the guidance strength multiplier to force compliance. Moving the image too aggressively off the manifold creates mathematical instability, pushing the sample into a state the denoiser can no longer correct. To address this, the researchers introduce backward guidance. This is a secondary mechanism designed strictly to prioritize enforcing the user's constraint over image realness. Instead of calculating a single nudge, the algorithm runs a multi-step gradient descent entirely within the clean data space. It optimizes the clean image until it fully satisfies the external network, identifying the optimal shift, delta Z0. This clean optimal shift must then be linearly translated backward into the noisy latent space of the current time step. Once translated, this new vector acts as a direct augmentation to the original denoising prediction. While forward guidance gently nudges the generation, backward guidance acts as a strict mathematical enforcer for prompt compliance. Combining these aggressive constraints introduces a final problem. Applying intense forward and backward guidance drags the sampling trajectory off the natural image manifold. When the data strays from this natural path, the generation exhibits bizarre artifacts that separate the outputs from natural images. You can see the breakdown here. With intense guidance and only one pass through the step, the constraint is met, but the structure collapses into an unrecognizable anomaly. The method resolves this using per-step self-recurrence. After applying the guidance, the algorithm re-injects random Gaussian noise and denoises that exact same step again. By repeating this cycle at the exact same noise scale, the artifacts begin to resolve back into organic shapes. This local exploration provides the algorithm the necessary computation budget. It searches the area until it finds a mathematical solution that satisfies both the external guidance constraint and the foundation model's natural prior. Self-recurrence serves as the vital optimization loop that reconciles harsh external demands with the foundation model's structural rules. These three mechanisms combine into the final workflow: estimate the clean image, optimize the trajectory using forward and backward gradients, and run the self-recurrence loop. Because the guidance networks are decoupled from the generation process, you can stack multiple independent loss functions simultaneously in a single pass. The model achieves highly complex outputs, like precisely positioning an astronaut on a horse while holding strict photorealistic constraints steady. And it holds up when pushed into deep stylized spaces, executing semantic text prompts with precise aesthetic control. There is a practical trade-off. Generation using universal guidance is slower than standard conditional generation. The time complexity scales linearly. Every recurrent step and every backward gradient loop multiplies the total inference time required to finish a single image. Universal guidance trades inference speed for flexibility, shifting the computational burden from training runs to individual sampling steps, and allowing a single model to support any differentiable guidance function.